having me. I'm happy to be here. So the pictures on this slide, I'm sorry, I say first, everything is joint with Gerard Benarouz and Paul Brigade, who are at NYU. The pictures are not exactly pictures of this model, but it's kind of the same phenomenology. So these are what I call landscapes. They're just samples of random functions. And for me, complexity means how many critical points. In like the Calculus 101 sense, derivative is 0. So these functions on the left have a lot of critical points, and that's what I call complex. These are complex landscapes. And there's a sort of phase transition as you go to the right. The ones on the right have fewer critical points, and those are not complex. That's simple for me. And I'm going to look at a particular example of these kinds of functions called the elastic manifold, and try to answer in different regimes, when do you look like the picture on the left, or look like the picture on the right. And sort of some notation, what I just said is like the picture, but in high dimensions. Okay, so I'm interested in Fn going from Rn to R, which is some sequence of smooth Gaussian random functions. Okay, so not like Brownian motion, really Calculus 101 pictures. And I call these landscapes. So for example, they could be Hamiltonians, disordered Hamiltonians in physics. Or if you like machine learning, they could be loss functions, right? Some empirical loss, which is random because it depends on data. So and the annealed complexity is I study the geometry of these functions through the number of critical points, which is a random variable because the function is random. So I take the expectation, take the 1 over n log limit. I'm interested in sort of large n exponential behavior. So crit fn in the whole talk is my notation for this number of critical points. And I call the limit sigma. Okay, so sigma is a real number, and this is a whole talk about computing sigma for a particular model. And just to rearrange, it says that the number of critical points on average is exponential in n, and the prefactor is sigma. Okay. So this is just for all critical points. You're also interested in, many variants of it, and one particular one today is sigma minimum, which just counts local minima. So not saddle points, not local maxima, but just local minima. And today I'm going to give you these for a special form of Fn called the elastic manifold. And I clarify, so this is the name of the model, but it's not a manifold in the sense of atlases and charts. It's a lattice model. And it's a classic model with two equivalent interpretations. The sort of first one historically is as a magnetic interface. But since this is a spin glass conference, I want to give another one which is sort of more spin glassy, which is that the model you can think of as being spin glasses interacting on some lattice. Let me explain, this is something you could do. Why would you want to do it? So I just copied over the version for minima. So especially in the case when Fn depends on some model parameters, right, either in physics or in data science. And as a consequence, this complexity also depends on the same model parameters. This is good for distinguishing regions in the parameter space, at least as a guess, such as in the case of physics where Fn is some disordered Hamiltonian. You would say that if your Hamiltonian has a lot of local minima, which are metastable states, this is my picture, lots of local minima, then you're in the sort of the glass phase. But if you have few local minima, so you kind of look like this parabola or whatever, then you're in a non-glass phase. Right? And this is just a guess. I'm not proving anything about free energy. You can do this later. But or in data science, if Fn is some empirical loss, and you want to minimize it with, say, gradient descent, stochastic gradient descent, you imagine that local minima can kind of trap descent algorithms. So if I have a lot of them, meaning sigma min is positive, so I have exponentially many, that's my sense of a lot, then it should be harder, and if sigma min is non-positive, it's easier. Okay, so the story is more complicated than this, but if you can compute this first, you can kind of start to guess how algorithms should work. And it's possible in this case, and people here know more about this than me, it's possible that the algorithm somehow escapes these, but that's sort of a more complicated story, and then also gets to be more interesting.
May I ask one question? Yeah. So you're computing the first moment. Is there some sense that this is representative?
Yes. So you could ask for the quenched version, right? So and essentially the deal is, so we know how to compute the version without expectation, only in cases where it matches the version with expectation. Basically. Yeah. In that case, that's a second moment computation. So Eliran has done stuff, Pax has done stuff. There is no model at all where we have a rigorous understanding of what this looks like when it's different from what the first moment tells you to. If you have ideas how to do that, talk to me after. Yeah, that's a serious question. So I told you the elastic manifold you can think of as spin glasses on a lattice. Let me start giving the picture. So you fix once and for all some lattice, which is your favorite one. So mine is whatever, this 3x3 thing. Any dimension, it doesn't depend on dimension. And I'm interested in putting spin glasses on this lattice. Okay, so what does that mean? I'll take continuous spin glasses, not easing ones. That's another sort of big open question. So for example, you can think of it as being some random function, f sg depends on n, going from Rn to R. You could do spheres or whatever, but I'll just talk about the case Rn to R. And how I'm going to attach spin glasses to this lattice is I'm going to start by putting at each lattice point some copy of Rn. Okay, right, so this is defined on Rn, so I need to have an Rn somewhere. So at every lattice point, I have a copy of Rn. And what I'm going to do is I write U for the kind of Rn at x in my lattice, and I'm going to evaluate the spin glass at U. Okay, so here's my Hamiltonian. This is sort of a preliminary version. Right, the easiest thing you could do is you just put spin glasses at every lattice point, and you just add them up. Let me explain a bit of what the dimensions are, show you this is actually in the framework. So U is my notation for, at every, U evaluates a lattice point and gives me back something in Rn. So U is sort of a function from lattices into Rn. So it's basically a point in some high dimensional space. Right? And this Hamiltonian depends on U and gives you back a real number. So it's basically a function from this high dimensional space into R. And it's a Gaussian random function on this space. So it is in the framework of some high dimensional Gaussian functions. Okay. This Hamiltonian, I just added them up. I didn't do anything interesting yet. That's why it's preliminary. It's a Hamiltonian for as many points as you have in the lattice of non-interacting spin glasses. Right? I like to draw spin glasses in this picture. And the lattice is dashed because at this point it doesn't actually appear. But the more interesting question happens when you add the lattice. So this is the Hamiltonian we're going to consider. And you add interactions in this way. Okay, so I take a sum over all pairs of points in the lattice. These are x's and y's. And I take the inner product of ux, uy with a certain weighting. So my weighting depends on t, which is an interaction strength. That's a parameter that you fix. And you fix some favorite interactions matrix. So you can pick one. I'm going to pick a certain one in a moment. I'll call this delta, because in a moment it's going to be Laplacian, but in principle it could be anything. And it has entries x, y. So it's a matrix indexed by points in my lattice. And if I have any 2 points in my lattice, this tells me how these should interact. Okay, so now this is a Hamiltonian. This is, the version with interactions is a Hamiltonian for spin glasses on this lattice. And I now filled in the lines because they now interact in some sense. Also, this will become clear in a moment. It's fine. Let's see. Cool. That went a lot better than I could have. What? Oh, it's connected up there. Ah. Thank you very much. Okay, the keyboard setup is nice. Cool. Thank you very much. Okay. What I was going to say is that this is a lattice model, and right, of course, if you just take a lattice to be 1 point, you just get a single spin glass back. So this is sort of a generalization in the lattice sense. Okay. So I've copied up my Hamiltonian here. This is a general thing, and the elastic manifold is one special case of this problem. So what's the special case? I pick delta to be the periodic lattice Laplacian. That's my interaction matrix. And I'm going to take these spin glasses to be this certain kind, which I'm going to call a soft spin glass. So this is some classical model. I don't think it's appeared too much in the conference so far. It's a 2-parameter model. It depends on mu, which is some mass, that's a positive number, and b, which is a disorder parameter. If you like data science, you can think of it as a signal plus noise model, if you prefer. So mu, I have mu times the norm of u squared over 2. This is deterministic. It's some parabola. And b times some noise. So I'm not going to be very specific about what the noise is, but basically it looks like this. Technically, it's an isotropic Gaussian function from Rn to R, and I have independent copies for every lattice point. So I have independent noise on all my lattices. And you can sort of see in the picture here, these are 2 parameters. This is maybe a signal-to-noise ratio or something, and when you add them, you get some kind of parabola, which is a bit wobbly, which is why I was drawing spin glasses like this. So this is some model. It's a classic analog of spherical spin glasses. And the interpretation, the way you say it's a spin glass, is that the components ui, which are real numbers, are spins, but they have this kind of soft quadratic constraint in the sense that if I sample from the Gibbs measure corresponding to this Hamiltonian at low temperature, then the norm is in some compact set with high probability, rather than sort of a hard spherical constraint where you force them to lie on the sphere. Okay, so it's another way of thinking about the same problem. It's, if you like spherical spin glasses, this is a way of putting it on all of Rn in such a way that it stays compact. But this is some classic spin glass. And the elastic manifold is the choice of this model where you take the delta to be Laplacian and the spin glasses to be these ones. So I said that if you take the one-point lattice, then you just have a single spin glass, there's no interactions. And the complexity of this sort of soft spin glass in that case was computed by Fyodorov. And the complexity of the spherical spin glass, which is maybe the better known analog, was also sort of the one-point version, was computed by Tuca and Girard and Yiji in 2013. And now we're interested in the lattice model, right? And let me emphasize that now I have a model that depends on three factors. So I have this T positive, which is elasticity. In the sense that to have low energy, you want things to be sort of flat. I have mu positive, which is a mass, and this wants that, in order to have low energy, you want all your u's to be close to 0. And B is some disorder that wants things to be rugged. And these are actually competitive terms. And so I cooked it up in this way, but actually the historical direction was to think about magnets. You're interested in sort of models that have some, models that are magnetized in some sense. And if there's sort of a plus region over here and a minus region over here, then there's some kind of rugged interface between these regions. And what was done historically was to say, well, this interface is sort of subject to the same constraints, but there's sort of there's an elastic term, there's a mass term, and a disorder term. So historically, this was cooked up as a model for interfaces between magnetic regions. But I'm just going to give the spin glass version here. So that's all I'll say about magnets. And these compete, right, in the sense of they want different things. And the question really is who wins, and that's why I have these parameters to scale, right? There are different ways you could ask who wins. We're going to ask in the sense of critical points. And they give you some degenerations, right? So if there's no noise, then the model is deterministic, and it's actually quadratic in U. So there's only one critical point, which is the global minimum, which is U identically 0. Whereas if T is 0, I said before, then there's no interactions, right? It's all these spin glasses. And via the sort of the one-point problem, it turns out that there's actually some critical mu, depending on the disorder, such that I have lots of critical points for small mu, for light ones, and few critical points for many. You can see this in sort of this picture here. So, right, mu is multiplying some parabola, v is multiplying some noise. If mu is very small, then the sum is basically still this noise, and so I have lots of critical points. Whereas if mu is very large, then it's basically a parabola. So that's a sort of reasonable seeming phase transition, and Fyodorov figured out exactly where it was. And in the lattice model, you start to see different things. So this is the main result. In the scaling where you take the fixed lattice, remember I said lattice is fixed for all times, and you take n to infinity, which in the physics literature is called the Mézard-Parisi scaling. So this is a three-parameter model, and for every u and v, in this limit, you get some complexity for the total critical points and some complexity for the minimum. And we're splitting this space, this whatever octant in R3, into what turns out to be the only two possibilities, which is either both the complexity of all the critical points and the complexity of minima are positive. This is an explicit thing, but it doesn't matter right now. Or they're both 0. Yeah.
I mean, this must depend strongly on the statistics of the noise, right? On
So
the correlation. If you take just and not on the correlation function.
So it turns out at the level of the first moment, it only depends on the noise isotropic function. It depends on some correlator. It only depends on this in a scalar way, which only depends on the second derivative of 0. For the quenched problem, that shouldn't be true anymore. You're absolutely right. For the quenched problem, it should actually depend in a very significant way on the correlator. But this was already present in the one-point problem, that the noise only appears as all that matters is. So for the talk, I wrote it by pulling out the second derivative of 0 and normalizing it. But for the quench thing, it's even in the one-point quench thing is open, figuring out how exactly it depends on this. Right, so the result is really about some boundary, some non-trivial boundary in this three-dimensional space. And actually, it's a fun way to look at it is looking at the kind of mu marginals. So I fix T and I fix B. And it turns out the mu marginals is some non-critical thing that's actually physically relevant. It's something called the Larkin mass. I'll talk about that in a moment. So let me give some remarks, and that'll be the end of the talk. So this confirms physics results of Fyodorov and Ludusal. And the proof relies on the Katz-Rice formula, which I won't write down, but it's a very standard way to reduce these kinds of questions about critical points into questions about, into this problem for random matrices. So I take Wn to be a real symmetric random matrix, which is related to the Hessian in some sense. I take the determinant and I take the absolute value. And I ask how the expectation of this guy scales for large n. Okay, so this is very well understood, but the question is really just how does this determinant behave? And I want to emphasize that we have sort of general techniques to answer this question for random matrices. And then if you push back through Katz-Rice, you can think of these as being general techniques to study the number of critical points. So I'm just giving you the elastic manifold for this talk, but we give sort of several more examples in the papers of these techniques, and they're meant to be kind of broadly applicable. And then the last slide here is that I said there's some random matrix. Well, what is it? For this problem, the random matrix that comes from Katz-Rice, it's a standard computation, is essentially a Gaussian random band matrix, W, plus Laplacian. It's not exactly true. The random matrix folks will say that the bandwidth is order n, so it's constant times n. That's the reason you have this scaling. It'd be much harder to do something smaller. And then let me say at the end this sort of thing about the Larkin mass. So the Larkin mass comes from the magnet story. So if there's some story of magnetism, didn't explain it in details. But one physical phenomenon in this story is something called pinning depinning. So it's some kind of phase transition people like to think about. It's related to some way you apply force to the model. And Larkin in 1970 proposed some simplification of the Hamiltonian. He said, okay, we want to study pinning depinning, so let's cook up a new Hamiltonian and see how that looks like. And the belief, as far as I understand it, is that Larkin's model is good only for some t's, mu's, and b's. And it turns out that it's actually exactly for those, such that the complexity vanishes. And one way to see that is that you can just check, Larkin's model basically linearizes the noise, so it has no local minima. It only has the one global minimum. It has no metastable states, and so this is, if you want, you can interpret this as saying that one reason Larkin's model stops describing things well is that it's missing all the metastable states. So let me stop here and thank you very much for your time.
Okay. Let's just take a question, otherwise I monopolize. So question. So I have a question myself. I mean, it concerns the question I had before. I mean, in this model, at least for statics, but also for Langevin dynamics, you distinguish two possible classes, either with long-range disorder or with short-range disorder. And I mean, with long-range disorder, you have full replica symmetry breaking. With short-range disorder, you have one-step breaking. It is very analogous to what you have in mixed p-spins, for example.
Yeah, sure. Yeah.
And in mixed p-spins, we know that there is a difference in when you compute the number of critical points, whether you are one step or full. So here, I mean, I haven't understood. I mean, if this second derivative condition that you have indeed corresponds to full one-step replica symmetry.
Yeah, I mean, I don't. So I don't have a great sense of this either. I mean, I think this is so. So I can write something. Right. So the model is a noise. Let me write this like this: noise of x. This is one-dimensional. No lattice. Noise of y. The expectation of this depends on some function b of these are n-dimensional. Dimensional x n s y n. Okay, whatever. Whatever the normalization is doesn't matter for some function b. So there's a characterization of what are the functions b you can put here that this makes a covariance. This is what you're saying. And in principle, there should be some functions b that are 1 RSB with some functions that are full RSB. And I have no idea which are which. I don't know if anyone knows. Maybe other people do here, but
It depends what you mean by you.
Sure. Yes, fair. Yeah.
Other questions? Thank you very much.